Okay, so we are recording now. Again, today's webinar is for learning about modeling evaporators in sugars. And the evaporators obviously represent kind of the heart of a factory in many cases, because they not only use the most steam, but they also provide vapors for other heaters and pans and processes. And they also, of course, process the juice to concentrate it up. So in a sugars model of a sugar factory, be it a cane mill or a beet factory, the evaporator station is a very important component of the entire model. And if the evaporator station isn't set up properly, the entire model is going to be difficult to balance. So that's one of the reasons we decided to go ahead and spend some time on it today. Just a little housekeeping to minimize background noise on our call today. If you're not currently asking a question, please mute your mic. But of course, then if you do need to ask a question, don't forget to unmute. The other alternative for questions is also to type them into the chat window and go to meeting. That works as well, and I can respond that way. So with that, let's go ahead and get started. I've started here with a blank canvas. So this is a completely blank sugars drawing file in Visio. And we're going to start from scratch, and we're essentially going to build a small evaporator train model here. And I'll talk about some of the tips and tricks and things that you want to watch out for as you do that. So obviously, if we're going to build an evaporator model, we need to start with a juice stream coming to the evaporators, correct? So I'm going to go ahead and take a connector here and come down in this area and add that to the model. Go to the pointer tool. Of course, I should put a station in first, getting ahead of myself. So we're going to use a pump. I'm going to use a large pump so we can see it. Okay, station number, I'm going to use 1000 because I want all of my stations on this page to be in the 1000 range. Okay, we'll come back to that pump in a minute. I wanted to start with the juice coming to it. Okay, here we go. So to add the juice, we need to give it a name because this is an external flow coming into the model. We need to name it. So this will be thin juice in. We'll need to specify the flow. This model is in SI units. I figured that was probably easiest for today, but of course you can change the units in your model using the default units setting. Let's go with a juice flow of 500,000 kg per hour, so 500 tons per hour of juice. This juice would be coming from a clarifier or filtration station most likely. Potentially softening or something of that nature, but let's assume that at this point the juice is at 80 degrees C. And if it's the overflow of a clarifier or it's an atmospheric tank of some sort, this juice would be at 1 atmosphere in that case. Now we just need to enter the flow stream components for the juice. So it's all liquid. There's no solids in this juice. So I'm going to use the dry substance impurity entry feature in sugars, so that we'll assume that this juice is at 12% dry substance and 85 purity. And when I do that, sugars automatically fills in the water content, the sucrose content, and the non-sucrose content in this liquid component section. So the next thing we need to do is select solubility coefficients, because there are both non-sugars and sugars in the same stream. Sugars will require us to select solubility coefficients. We're not going to be crystallizing anything in today's model that we're building, so it really doesn't matter which ones we choose. I'll choose group beet solubility for right now. And that is everything we need to start with for our thin juice coming to the evaporation station. So I'm going to go ahead and click OK. Now back to this pump. I'm going to go ahead and give it a name. Thin juice pump. And the reason I put a pump here is very important, and actually is something that a lot of people forget when they're modeling in sugars, if you remember a second ago, I set the pressure of that input juice stream to 1 atmosphere because it was coming from an atmospheric tank or a clarifier overflow or something of that nature. The first thing we're going to do after this pump in the model is we're going to start heating that juice, and then we're going to put it into an evaporator. And evaporator preheaters typically raise juice temperatures up to 120, even 130 degrees C. But if the juice is only at atmospheric pressure, it will begin to flash inside that inside that heat exchanger. So that's why we need to insert a pump station into this model to raise the juice pressure so that we prevent flashing in juice preheating prior to evaporation. We don't want juice evaporating until it's actually in an evaporator. That would cause errors in the model if it's flashing in the heater. So let's go ahead and raise the juice pressure to 350 kPa. And just so we can keep track of what it is, I'm going to put the juice on the product layer. And let's zoom in, get a little closer here. Now you can see that it turned green. That'll help us keep track of what juice flows are. They're on the product layer and they'll be green. We can also add a label here. Oops, I was selected on the flow. Let's select off, select on the canvas. Now add a text box. And this will be juice in. And perhaps because this is a major important input, we'll make it a larger font, maybe 18-point font. Okay, and we can also view the conditions of the juice on the screen using a flow legend. So we'll add flow rate by weight, pressure, temperature, DS, and purity. So now we have all the information about that flow displayed on the screen. Okay, as I mentioned a second ago, the next thing we need to insert is juice preheating prior to the evaporators. So we'll go to the heat exchanger shapes, and we'll drop a plate style heat exchanger on the model. And this heat exchanger that can be station number 1100, that's fine. We'll go ahead and double click, give it a name, juice preheater. And let's say that we are going to increase the temperature to 120 degrees C. Okay. Now, all we need to do to connect the juice is copy and paste the juice flow stream that we already had. That way it's already on the product layer. We don't have to adjust that. And then it's connecting those two stations just as it should. Let me zoom in a little bit so you can see that better. We needed to connect to the input port for juice to the heat exchanger. So we did that. The heat exchanger also needs some steam. So let's go back to the connector tool and add a new flow stream. And we'll go to layers. We'll put that on the steam and vapor layer. Now you can see it's red. Now I'll double click. And we need to name this steam. So this would be preheater vapor. And give it, we don't need to give it a flow because the heat exchanger station is going to back calculate the flow. It's going to be a required flow that it's however much is required to heat the juice to the specified temperature. We can leave that 0. Sugars will calculate it. However, we do need to specify the temperature and pressure and the components. We know it's 100% steam, so we type that in the gas component section. We know the pressure, let's say, is 160 kPa, maybe more, 200 kPa. But I don't know the temperature because I don't have my steam tables right now. But that's okay. If I leave the temperature at 0 and I specify 100% steam and a pressure of 200 kPa, if I click OK, this box pops up and Sugars tells me that it has calculated the temperature and pressure to saturation conditions. And you can see here 120.2 degrees C saturated steam temperature for that pressure. Now, one thing I noticed is this is only just barely higher than the pressure, or the temperature that I specified in the heat exchanger at 120. So it's probably not going to be achievable. So I should lower this to 115. Okay, so let's go ahead and give that a label as well. I'll just go ahead and copy. That was Control C, by the way. I can't see my keyboard. Oops. Okay. I got something I shouldn't have. I accidentally copied the entire drawing. Delete. Okay. Let's try this again. Copy. Paste. Much better. Okay. Steam. Okay, so the heat exchanger has steam now. It needs condensate leaving, which would be the output port number 1 over here. We'll put that on the water and condensate layer. And now we have only one connection left on the heat exchanger, and that's the juice output. But before we do that, I want to go ahead and drop an evaporator on the diagram. Now, this is a somewhat simplified version. In most cases, you would have multiple preheating heat exchangers before an evaporator train. But to keep this as simple as we can for demonstration purposes, we'll just use one evaporator preheater. So I'm going to come over here to the evaporation shape stencil. And you'll notice there are a whole list of evaporator station shapes over here. Everything from Roberts and Calandria evaporators to long tube and falling film plate evaporators. What you need to know is that all of these evaporator shapes represent the same sugars calculation station. They're simply different pictures so that when you're building a model of a factory, the visible picture on the drawing represents the type of evaporator that you are modeling. But all the calculations for all of these are the same. I'm just going to use a regular Roberts evaporator for the demonstration today, but you could use any of them and they would perform the same calculations. Okay, so station number 1200, yes, that's fine. Now let's give it a name. So this will be the first effect evaporator. And there's other settings here in the evaporator properties, but I'm not going to set those quite yet. We're going to continue building the model. Oh, it's going to require me to set the pressure. I always forget that. So let's say a vapor out pressure of, let's see, 250 kPa. Okay, now we have an evaporator. Now we can connect the juice from the preheater to the evaporator. Let's go ahead and copy and paste juice flow stream to the evaporator. Now I'm going to reroute this a little bit so that it's a little cleaner to look at. There we go. Okay, so now we have juice from the preheater to the first effect evaporator. Today, for this demonstration, I'm going to make a 3-effect evaporator train. And I know that's a small evaporator train. Normally, they would have more like 4 or 5 or even 6 or 7 effects. But once you learn to make a 3 evaporator train, you can make as many effects as you want in sugars. The process is the same. You're just adding more steps. So let's go ahead and add 2 more evaporator vessels to the drawing. All right, this one will be 1300, and we'll name it second effect. And the pressure of this one, we will make 150 kPa, and then one more. Station 1400, third effect evaporator, and this one will be under vacuum. So we're going to give it a pressure less than 1 atmosphere, we'll say 50 kPa. Okay, now we can go ahead and connect the juice flows from one evaporator to the next. So I'm going to go ahead and copy, and paste. So I'll connect the juice outlet from one evaporator to the juice inlet to the next evaporator. And then the same again, copy, paste. And looks like I didn't get them quite the same distance apart, but that's okay. All right, and for the sake of visibility, let's add flow legends to these. Weight, DS, temperature. That one can go here. So that's the juice feeding the first evaporator. And you'll notice because we haven't balanced yet, all of these are going to be the same because I copied and pasted flow streams. These will adjust to their actual values after we balance the model, but we can't balance, of course, until we have everything built. So now I'm going to just add flow legends for all of these. And I suppose we do also need a juice outlet from the last effect. So I'm going to go ahead and copy and paste. Connect that to the outlet of the last effect, and we'll just point it straight down. Give it a flow legend. Weight, DS, temperature. And I'll also give it a label. Copy, paste. This is juice out, of course. So now we've added all of the stations that the juice passes through in our 3-effect evaporator station. And we have all of the juice flows connecting those stations. So step 1 complete. But that was the easy part, unfortunately. Now we have to deal with the steam, vapor, and condensate. So I'm going to go ahead and start by adding steam to the first effect evaporator, because obviously we need steam coming in to provide heat to the whole system. So I'm going to copy and paste the steam flow that I had already. And I'm going to go ahead and give it a label. Copy, paste. This is exhaust steam, which would typically be your turbine exhaust, depending on your factory. Now we need to specify this steam flow. Let's open the properties by double-clicking. We'll rename it here, exhaust steam. And again, we're going to leave the flow 0 because Sugars is going to calculate the steam required to perform the evaporation that we're going to have in this evaporator set. So we're going to leave the flow set to 0. However, in this case, this exhaust steam is at much higher pressure. Let's say somewhere in the neighborhood of 400 kPa. Now, if I click OK, and I'll set the temperature back to 0 because I want Sugars to calculate saturation conditions again for me. And your exhaust steam may or may not be saturated. Let me go back to that. So the temperature calculated was 143.6 degrees C. And that's saturation conditions for 100% steam at 400 kPa. Exhaust steam might have some superheat, and if you do have a temperature measurement on your exhaust steam coming to your evaporators, then you should enter the actual temperature of the exhaust steam. But if you don't know the temperature and you don't know how much superheat, assuming saturated steam at this point is pretty close in most cases. Okay, so now we have the steam coming to the first effect. Obviously, we're going to need condensate leaving the first effect. So let's go and copy that other condensate flow we had. You notice I do a lot of copying and pasting in Sugars, and that's simply to save time. When I already have streams that have the correct layer and they're roughly the correct specifications and things like that, then I'll use copy and paste just to speed things up instead of drawing a new connector every time. Okay, so now we have everything except for the vapor outlet connected on this first effect evaporator. And this is where one of the tricks to modeling evaporators really comes into play. Now, the first thought you might have would be to directly connect the steam from the first effect to the second effect, because that's how the steam travels through an evaporator train, is from higher pressure to lower pressure, from one effect to the next, down through the train. But there's something to keep in mind, and that is the fact that usually there is a steam header between the evaporator effects, meaning that some flash tank flows or other steam flows might come in and join this header, and also vapor draws are going to be taken away from this header, going to heat exchangers, pans, other users throughout the factory. So the way to deal with that in sugars is to go to your miscellaneous shapes, and you want to include both a receiver and a distributor station in between each evaporator's effect. So I'm going to come here, and I just picked up a receiver station. I'm going to drop that on the diagram. Now, I don't want that to be station number 1500, because that's in the process between evaporator station 1200 and evaporator station 1300. So I'm going to make this station 1240, because that puts it in between those two numbers. And for those of you who may not remember, station numbers determine the calculation order when balancing a sugars model. So we want to make sure that our station numbers generally increase as we pass through the process, so that sugars is calculating the balance in order of process flow. Okay, I'm going to go ahead and name this receiver. This will be first vapor receiver. Now I can connect the vapor outlet from the first effect, copy and paste, to this receiver. And then the next thing I'm going to add is a distributor station. So the receiver, okay, the distributor, let me back up. The distributor station number, again, we want it to be in between this receiver's number and the next evaporator effect, because that's going to be the flow direction of the vapor. So we have 1240 on that receiver. Let's use 1250 on this distributor, and we'll name it first vapor distributor. And again, we need to connect the steam from the receiver to the distributor. So the purpose of this, again, is the receiver allows us to bring other vapor streams into this header. So for instance, and we'll do it in a little while, if you had a flash tank here flashing the condensate, you would want the vapor from that flash tank to come to this receiver. And then the distributor allows us to take vapor away from this header. So if we have a pan or a heat exchanger or some other steam user that uses first vapor, we can use this distributor to supply that vapor to that other user. It's always good practice to put both a receiver and a distributor station in the vapor line between each evaporator effect. That way, no matter what you need to connect to it, you have the ability to do that. For now, I'm going to go ahead and connect this distributor station to the next evaporator effect. So copy and paste. And this will take just a moment, but I'm going to go ahead and do the same thing to the second effect. So I'm going to copy the condensate and paste it, connect. And then I'm going to copy both of these two stations and paste. Now notice we'll need to give them new station numbers, so we'll use the same convention we used before, 1340 for the receiver and 1350 for the distributor. Over just a little bit. And now I need to do the same thing, copy and paste to connect from the evaporator outlet to the receiver, and also from the distributor to the third effect evaporator. Now we have vapor traveling from the first effect to the second effect, and from the second effect to the third effect, and we've given ourselves the ability to both insert vapors and remove vapors from both headers by using the receiver station and the distributor station in between each evaporator effect. And again, I'll just repeat, even if you don't know right now what you might need to connect or take away from this evaporator, or this vapor header, it's a good idea to put these stations here so you have them available and you can make that adjustment later if necessary. Okay, now we need to set send the vapor out of the final effect. So I'm just going to copy and paste a vapor flow stream, and also the condensate from the last effect. Copy and paste. I don't want to connect it to the flow legend. There, let's move that. Okay, now let's add a few flow legends so that we can see the values of these flow streams. So weight, temperature, and pressure for that one. Let's go ahead and look at weight, pressure, and temperature for this in between the receiver and the distributor, and I'll do the same thing over here. Weight, pressure, and temperature. And for the vapor leaving as well, weight, pressure, and temperature. Okay, now we have all of the flow streams connected to all of the required connection points on the stations that we have in this model. Every evaporator has juice in and juice out, steam in and vapor out, and as well as condensate out. So we're almost ready to balance this model, but remember, whenever we set up these evaporators to begin with, I kind of skipped over some of the settings. So we need to go back to them, and I want to show you why I skipped over them to begin with. We did set the pressure. What we didn't set is this effect number setting right here. Now for the first effect evaporator in the series, obviously effect number 1, first effect, is correct. So we'll just leave that as Sugars has put it here. However, for the second effect, we'll come here and notice that if I click this little drop-down menu, not only do I have the choice to make this a first effect, but I also have the choice to make it effect number 2, which is the station after, or the effect after station 1200. So if I select that, now I've told Sugars that this is an evaporator train, and this evaporator station should be balanced in coordination with the first effect. And of course, I can go to the third effect. Oops, there we go. And I get the same choice, except this time I get a 3 with the third effect option here. Now this only occurs if the evaporators have juice flows connecting them in series, just like we've done. If these were not connected, we would not have the option to set them up as a 3-effect evaporator train. So I'll go ahead and click 3 for third effect after station 1300. Click OK. So now we've told Sugars that this is a 3-effect evaporator train, and we've told it what the order of the effects is, and Sugars will calculate the balance for these evaporators in coordination with one another to balance both the vapor flows and the juice flows through the set. Now there's one more thing that we need to do before we can balance this model. Sugars needs to know at some point in the evaporator train what the specified juice dissolved solids content should be. You can set that in any effect, but typically, and this is I think typically the case in actual factory operation, you want to set the total solids content in the last effect of the evaporator train. So I'm going to go ahead and tell Sugars that I want 68% total solids on this flow out. This would be the juice flow out from this evaporator. I'll go ahead and click OK. Now I want to show you what happens when I do that. Notice that now, if I click on the other evaporator stations within this train, the total solids option is gray. And the reason for that, same thing on the first effect, the reason for that is because there's only 1 degree of freedom in a coordinated evaporator train. So you can only specify the actual dissolved solids of the juice in one of the effects. The rest of them will have dissolved solids content as a calculation result of the amount of steam required and the vapor draws and everything else that's going on in that model. So for this case, and I think in most cases, you want to specify that total solids on the final effect, and that'd be the only place that you can specify the total solids content in a multiple effect evaporator train. Okay, I believe we're ready to balance this model. So I'm going to come to my sugars menu up here at the top of Visio, and we will find out if there are any errors, because sometimes things don't get entered quite correctly, but let's find out. No, it looks like we have a clean balance. So you can see that sugars calculated the exhaust steam required to evaporate the juice flow up to 68% dissolved solids, and it also calculated the vapor flows in between each effect and the juice flows and solids contents in between each effect. And again, remember that it's balancing this sequential flow of both vapor and juice, so the dissolved solids content in between each effect is nothing you can specify. It's just a result of the calculations and the balance. Looks like I forgot to put a flow legend on this steam flow, so I'll go ahead and do that. And drop that here. It looks like it required 31,500 kilograms per hour at 200 kPa to heat that, to preheat the juice. So now we have, what we have here is pretty much an oversimplified version of an evaporator set. There are other things that we can do here that will make this more realistic to what's actually happening in a factory. So I'm going to go ahead and delete this steam flow right here, because we're going to use vapor draw from first vapor to supply steam to this heat exchanger. And the way I want to do that, to keep the diagram clean, we could use a regular connector, connect it to this distributor station, and have it run all the way around and back over here to this heat exchanger. But when you start running flow stream connectors that long, snaking all over your page, it starts to make the page hard to read. So I'm going to use what's called an on-page connector in sugars. And this is a connector that allows us to put a flow stream between two stations without having a line running all across the page between them. Okay, so I'm going to go back to home and put this connector on the steam and vapor layer. And you notice I connected the back side of the arrow, zoom back in a little bit, to the connection point on this distributor. If this is my first vapor header, that's where I want to get the steam. Now, with a cross-page connector or an on-page connector, they work the same. All you have to do is copy, and then come to the place where you want it to go. I'm going to go paste, and connect to that. And sometimes these on-page connectors have a little bit of an odd routing in Visio, but I'm going to go ahead then and flip it horizontal, connect to that side. Oops, do that. Let's just disconnect. Okay, you know what? I'm going to start all over because I've got myself messed up here. Okay, we're going to come back here, copy. It's best to do that flip first. I should have done that to start with. Flip horizontal. There we go. Now it's pointing in the right direction. And now I can connect it directly to the heat exchanger. And you notice the number right here in this connector. It says station 1250, output port 5, and that's telling us where it comes from. Station 1250, output port 5, which is the one right in the middle. And this end of the on-page connector shows where it's going to, station 1100-1. The heat exchanger is station 1100, and the steam input is input port number 1. So I'll go ahead and add the flow legend back to it, so you can see, and we'll put it up here just as mass flow. And then we can add a label. Copy, paste. I don't want it to be that big. Maybe 12. Let's say 2 preheater. And then put that right here so that we remember that this vapor draw goes to the preheater. And now we can rebalance the model. Full balance. And you can see that the exhaust steam requirement has increased because now we're taking a vapor draw off of the first vapor header and using that vapor to heat the juice in the preheater. And you can do the same thing with vapor draws to pans and other heat exchangers off of each header in between each evaporator in the train. So very useful thing to be able to do in sugars, because almost every sugar factory is set up that way, and it's important to get the correct vapor headers connected to the vapor users so that the evaporator balance is correct. The other thing you'll notice is that the dissolved solids content changed slightly in the intermediate effects between 1 and 2 and between 2 and 3. And that's because here we have a vapor draw, so the first effect is doing more evaporation now, and the second effect is doing a little bit less. But sugars handles all of that because it knows that this is an evaporator train, and it needs to coordinate the balance of all 3 of these to achieve that final dissolved solids content of 68% DS right there. Okay, there's a couple other things I want to show before we finish up today. One would be a flash tank. So let's go to evaporation shapes and flash tank 1. So typically evaporator trains have flash systems to flash the condensate down to the next vapor pressure and recover some heat in the form of flash vapors. So you can see this one that we're going to put in place after the second effect. It's going to take the second effect condensate. So we need to have the station number after the second effect station. So I'm going to use station 1320. So it puts it right after 1300, which is the second effect. Okay. No, I didn't give it a name. Let's go ahead and name it. I'll call it second flash. And I'm not going to set any other parameters in this flash tank right now, and I'll explain why in just a minute. Let's go ahead and connect the condensate from the second effect to that flash tank. Now we have 2 other outputs. Zoom in. 2 other outputs from a flash tank, one being the condensate leaving the flash tank. So let's go ahead and copy and paste and connect right here. I don't want that pointing into my juice out label. Let's go ahead and give it a flow legend. Weight, temperature. And we also need a vapor flow connecting the flash vapor outlet to the second vapor receiver up here that we installed. And that's why we put that receiver in. So let's copy, paste. So from the vapor outlet of the flash tank to the receiver up above. We'll go ahead and see, we'll add a flow legend just to see how much vapor we're recovering from this flash. And remember, the flow legends are not correct until we balance. Okay, so the reason I didn't specify anything else in this flash tank is because flash tanks have a little setting for the vapor out conditions called pressure feedback. If the pressure feedback box is checked, as this one is now, then sugars will read the pressure of the header that the vapor is entering. So this station 1340 up here, whatever that pressure is, will get fed back through the calculations to the flash tank 1320, and then it will flash to those conditions. And that's very useful because if you're making adjustments in the model and you end up with a different pressure leaving the second effect here, then the flash tank will automatically adjust and match that pressure, which is, of course, in the reality in the sugar factory is exactly what happens. The flash tank runs at whatever pressure it's connected to in the header above. So let's go ahead and rebalance the model. And what you can see is that condensate, by flashing, reduced the temperature down to 111 degrees C, but we recovered about 3,600 kilograms per hour of steam back to the second vapor header. So you can set these flash tanks up between each evaporator effect that you actually have a flash system in the factory, and using that receiver station that I was stressing earlier is important, then you add that vapor back into the proper header, and Sugars handles that well. So the last thing I want to show everybody on this webinar is adding a condenser to the evaporator train. So let's go ahead and go to cooling shapes. And for this case, I think we'll use a contact condenser. You could use a non-contact condenser as well. Drop that on the model. Now this is the last thing in the evaporator train. So we're going to go ahead and give it station 1500. That's fine for a number. And we need to name it. So let's just say evap condenser. And of course, the vapor from the last effect simply gets connected to the vapor inlet on the condenser. And then the condenser needs cooling water. So let's copy and paste a water stream. And now we'll give it a label. Copy, paste. This will be cooling water. Now let's specify this stream. Oh, we have to give it a name because it's an external input flow. Remember, any external input flows to the model must have names. So this is cooling water. I'm going to set the flow to 0 because I want Sugars to calculate the flow based on the condenser's needs. So I'm going to clear out the flow value that was there. The pressure, let's say this is a cooling water header, is probably going to be at least 300 kPa. Depending on the system. And the temperature of this cooling water is 20 degrees C. Probably coming from either a cooling tower or a cooling pond. And let's go ahead and put flow legend, weight, and temperature. Now we need a way for the water to get out of the condenser. So simply copy and paste a flow stream and connect it to the water outlet. And let's go ahead and put a flow legend there as well. Weight and temperature. Okay, so now we have the condenser to condense all of the vapors leaving the last effect of the evaporator train. I believe we're ready to balance. Oh, hang on, let's look at the settings of the condenser. So the internal pressure of the condenser can be set. And then you can also set several different options for how much water is required. First of all, let's set the internal pressure. We know that the evaporator vapor is at 50 kPa, so let's set it the same. You could put it slightly lower if you know that there's some pressure loss between the evaporator vapor header and the condenser. Minimizing the cooling water to condense all the vapor is the simplest way to set the flow. But you could also choose a specified quantity of cooling water, or a specified ratio to the vapor flow, or even to control the outlet temperature of the cooling water or the approach temperature of the cooling water to the vapor temperature. I'm just going to leave it here on minimizing cooling water. That's the simplest way to do it, and the way I recommend at least starting your model. So I'm going to click OK, full balance, and you can see that all of the vapor is condensed with a cooling water flow of about 1.2 million kg per hour, so 1,200 tons per hour of water. And the outlet temperature is 81.3 degrees C. Now, that's an extremely efficient condenser. In most cases, contact condensers are going to have much lower outlet temperatures. So that's where we could come here and say, well, I actually measured the temperature in the mill, and it was actually 60 degrees C. Now, if I click OK, run the full balance, now you can see that it actually requires more cooling water because the condenser is not as efficient. The outlet temperature is actually lower. And so that's what you can do if you have that measurement available to you. Okay, so there we have a simple evaporator train completely built. Sorry for that, just zooming out a little. And all the basic elements are here. One more thing I want to show you is with evaporators, similar to heat exchangers, you have the ability to set the heat transfer parameters instead of setting the vapor or temperature parameters. Now, I don't recommend doing that for the first pass through a model. When you first build a model, simply set the vapor temperature or the outlet flow, or excuse me, the vapor pressure or the outlet flow temperature of the evaporator, and let the model balance with constant values there. However, if after you have the model put together and everything is balanced, you want to look at the heat transfer performance of that evaporator, you can come here, and if you know the heat transfer surface area, let's say this one is 3,000, you can click on coefficient and calculate a heat transfer coefficient. And then if you click OK, sugars will fill that in the box here. Now, because we've specified a heat transfer coefficient and a heating surface area, instead of maintaining a constant pressure and temperature of the evaporator outlet, the sugars calculations will determine what the evaporator performance will be based on these coefficient and surface area. So I'm just going to click OK now, and you'll see that if I balance the model again, nothing changed. The exhaust steam flows were the same, the dissolved solids content was the same, the pressure is the same, 250 kPa, because all I did was change the specification, but I didn't change any of the inputs. However, let's increase the juice flow to 550 tons per hour. Now, the first effect has its area and heat transfer coefficient specified. Remember, we specified these here. The pressure and temperature are variable now. So if I balance again, now you can see that the pressure went down on the outlet of the first effect. And the reason for that is because now we've put a greater evaporation load. We increased the juice flow. There's a greater evaporation load on the first effect. And to achieve that greater load at a constant heat transfer coefficient, we needed a greater delta T, a greater temperature difference. That's why the temperature and pressure of the vapor out and the juice out are lower now, to achieve a greater temperature differential. And again, this is a little bit more difficult to balance the model this way, so I suggest only trying this after you have the model balanced with constant pressure and temperature settings. So I'm going to go back to 250 kPa, and it automatically calculates the saturation temperature. Click OK and rebalance, and now we're back to constant pressure settings. Okay, well, I know that was very fast and furious, but we just built an entire evaporator train in less than 1 hour. So at this point, I'd like to open it up to questions from anyone who's signed in. You can either unmute your microphone and ask verbally, or you could type a question in the chat window. And any questions you have, I'll do my best to answer.
Hello, Scott. You hear me?
Yes, I can hear you.
Yeah. Good morning, everyone, and thank you for your good presentation. Still, I'm asking you: is the evaporation trend is not considered the boiling point, the hydrostatic heat loss? Still, yeah, working on it because to optimize the evaporation plant as a designer or as a new plant. Sugar is still lagging for that part. So, yeah, addressed this one this year, or because the
Yeah, thanks for the
temperature.
question.
Yeah, go ahead.
Yeah, so actually what we're right now our development focus is on the new release of Sugars 4.1,
Yeah,
which is to basically modernize the code. But in the meantime, I actually have already built the calculations necessary for exactly what you're talking about, which are the hydrostatic head boiling point rise considerations for evaporators, just like these Roberts evaporators here that
yeah.
have a submerged heat transfer surface area. So we have the calculations built, and our plan is in the next release, so not this very upcoming 4.1, but in 4.11 or whatever number it ends up being, then we will incorporate those calculations into the Sugars code and test them and put those out in the release. So that improvement is coming. We know about it. We've done the calculations. We just need to get it into the code in a future release.
Thank you, Scott. Thank you.
Thank you. Any other questions today? Okay, I have a chat window question from Raul. If I'm reading the Spanish correctly, he's asking if this program is in Visio, and the way Sugars works is the drawings are developed and put together in Visio, and then Sugars runs a calculation routine as an add-in of sorts behind the scenes when you balance it. So you use Visio, and you have to install Visio, and you use that to build the drawings, and then all the Sugars stations and flow streams in a Sugars drawing are connected to the database and the calculations of the Sugars program, which occur when you click the balance button. So yes, Sugars uses Visio as its drawing platform. Okay, we have another question here. I would like to know, how can I do the Brix curve and show it on the page? Okay, so I'm assuming by Brix curve you mean these numbers. Let me zoom back in a little bit. These numbers here, so it was 12 on the inlet, and then 17 between the first and second, and 26 between the second and third, and 68 out of the third. And to answer your question, these flow legends are the best, simplest way to show these parameters on the screen. You can also use custom fields, which we have another webinar that we did a while back on displaying custom parameters on the page using fields, and you can even do calculations and such. So if you go to our YouTube channel, you can see that. I see you're asking also to show it as a graphic. I'm not sure if that's really something that's possible. The only way I can think of to do it would be to put an embedded Excel spreadsheet on the page and reference those values, and then build an Excel graph and keep that embedded on the Visio page so it shows up next to the drawing. I've never personally done that, but I suppose it is possible. So I would suggest you try that. Okay, we have a few more questions here. how can we balance if we have the heating surfaces of the various bodies and know where we are missing for steam percent cane? Okay, I'm not sure I understand the question. So I did, if you know the heating surface areas, then you can determine the heat transfer coefficients after you've balanced, or if you already know the heat transfer coefficients, that's right here. You can enter them. So basically, I'm not sure I've answered the question very well, but I'm not sure I understand the question. If you could rephrase maybe, or maybe I've already answered it. Let me know one way or the other.
Maybe he can calculate the enthalpy for each evaporators, then he can do the steam on cane ratio.
Yeah, and when you go to the heat transfer coefficient calculation page right here, I've just brought up, it actually does show the heat transferred for each evaporator, so you can see that number here if you need to use that. Okay, I have another question here from Chris Gordon. How do you set up the balance if you have evaporator bodies in parallel? So that's easy. You basically build the drawing as though as they exist in practice, and you can actually essentially set up one of the evaporators that's in parallel at constant steam flow, and it will take us that portion of the flow, and then the other evaporator would be one of the effects in series. So you can only specify one evaporator for each effect, but if you have two in parallel, if they're exactly the same evaporator and you know that they're connected the same way, then the simplest way to do it is simply to assume that they are one body and then use double the heating surface area. But if you need to show them separately for whatever reason, you'll just need to set up one of the evaporators that's in parallel with a constant flow through it, and the other one will adjust based on the series balance. Okay, so I have another question here. I've been doing the evaporation balance, but I separate the pre-evaporator, inter-evaporator, and triple effects in order to make the simulation like the plan is. My question is this: does this make some change in the balance? No, you can separate evaporator trains into different segments all you want, and that will allow you to put different dissolved solid set points in the different sections. The only thing to keep in mind is that then you need to make sure that you're separately balancing the steam supplying those segments, because they're not going to coordinate their flow of steam from one to the next if they're in separate sections. Okay, another question: is there a difference between a central downtake design compared to an eccentric downtake? In some old installations is the case. So again, going back to earlier, if you go to the evaporation shapes stencil here, all these evaporator pictures are different shape pictures to show the different types of evaporators, but the calculations are currently the same. Now that may change to some degree, or at least give you the option to change that whenever we move to what Fick was asking earlier, which is accounting for the hydrostatic head and the boiling point rise. But for now, all of the evaporator station types use the same calculations. Okay, what is the difference between doing evaluation and make some simulation for design? Well, that goes back to really what I was talking about earlier as far as how you set up the model initially. If I'm doing an evaluation of a factory that's already existing, then I may already know the heat transfer coefficient and surface area of each evaporator. So I may go ahead and enter those values and balance the evaporator with constant heat transfer coefficient in surface areas. And then we're going to see the pressures and temperatures vary like I showed you. But if I'm designing a new evaporator train, then I'm going to set the pressure and temperature profile to what I want to design for. So I'll make those constant here, and then later I might figure out what heat transfer surface area I need based on an industry standard coefficient for evaporation. So that'd be the difference between evaluation and design and simulation. Okay, Mr. Zamora is interested to know where he can get the program. So if you go to our Sugars International website and send a request, we can provide you with a quote. And okay, looks like everyone is, thank you there. So any more questions at this point? All right, well, thanks everyone for joining. We did record this, so we will make the recording available on our YouTube channel for all those who have watched and anyone else who may want to tune in and check it out. We will continue to do these training webinars periodically as we go forward, so any suggestions you have for things that you're interested in, topics you'd like us to cover, please let us know. Otherwise, thanks again and have a great day.